Hello friends, welcome back to the tetrahedron chemistry classes. So in the name reaction series, today I am going to discuss a very important reaction. The name of the reaction is the Favoroski rearrangement, and this reaction is actually of immense importance in organic synthesis. That's why from this topic in the competitive examination, questions are generally there, whether you are going for your CSIR net examination, GATE examination, for your IIT JAM examination or your JEE examination, right. See, in every examination you will find the question from here. Okay. So today we will see this Favoroski, the detailed things about this Favoroski rearrangement, okay, and we will solve more than 15 different types of the problems based on this Favoroski rearrangement, which actually people generally miss in their lectures, okay. And there is, see, generally what happens, you actually read a certain type of the mechanism from somewhere, okay, and you find little bit of confusion. Then if you don't have the proper resources and you don't have the proper literature, then obviously you will have the various doubts. And even in the lectures of the others, if you have already watched the lectures of on this Favoroski rearrangement from some other sources, then after the end of this particular lecture you will find, okay, those lectures actually misses the various concepts here, various things here. So today I am going to discuss this Favoroski rearrangement in pretty much detail, with every possible aspect actually, right, which I am going to explain today. So the length of the video will definitely higher this time. It will go beyond 1 hour actually, right, but you will learn lots of things about this Favoroski rearrangement, okay. So as you can see, some of the things which I have already written on the slide, because it is very important, because otherwise the length of the video would increase very much, okay. So what is the Favoroski rearrangement? You can see in the Favoroski rearrangement, your substrate would be α-haloketones. That means you will have the ketones, and that ketone on alpha carbon will have the halogen, okay. This is the thing which you will need to know. And when these alpha-haloketones are reacted with your alkoxide ion, it could be your methoxide, it could be your ethoxide. So when it reacts with this alkoxide ion, it will produce ester, and when you actually use that purely basic medium, right, this nucleophile, this base as the nucleophile, okay, then what will happen in that case, or nucleophile, or the, you can say, the base, right. So in case of the OH negative, you will end up with this product, that would be your acid. And if you use this nucleophile NH2 negative, then this will give you the amides, okay. So these three possibilities are there, but in the examination, I actually see, I have gone through the various questions from the different examinations. They generally ask the question from this ester part or the acid part. However, they hardly touch this amide part, but this amide part is already quite open for the question from this amide part, actually quite open for the upcoming examinations, okay. So this thing actually you should remember. Now one more important thing, this alpha-haloketones may be your say simple aliphatic straight chain, or say your open chain, right. And when they have actually this open chain structure, or simply, right, then you will have these things, right. But when you have this alpha-haloketones in the cyclic form, and that ring, if it in itself is if containing that carbonyl group, when this happens actually, that means the carbonyl part is the part of the ring. When you take this substrate, right, and obviously this is your alpha, if I can write, then it would be, say, your alpha carbon, and this is also your alpha carbon, and this alpha carbon is having your halogen substitution, and it cannot be always the halogen, it could be any leaving group. So it's better to say this X as the leaving group. So what I can do, I can write X as the leaving group. For leaving group, I am writing Lg, and that leaving group could be anything, okay. This could be your chlorine, this could be your bromine, this could be your I, okay. Of course, the leaving ability would be different for Cl, Br and I, and so does the rate of the reaction would also be different, okay. And you may have your this tosylate OTS, right, and you may have the OMS, okay, and you may have this triphthalate OTF, okay, and you may have some other type of the, like this doubly bonded Br, Ll bromide, okay, and then you may also have this 3-membered ring, epoxide, right. So all these actually can be present in the substrate as the leaving group. So you should know actually. So X is not the halogen, right, but primarily the reaction actually was studied using that haloketones. That's why the Favoroski rearrangement is known as the base induced rearrangement of the alpha haloketones to the carboxylic acid derivatives. Okay. But you may have any leaving group in it. Okay. And you see here, if you see this one, what will happen when this ketone is the part of the ring, then the ring contraction would occur. Your 6-membered ring will convert into the 5-membered ring, and 5-membered ring will convert into the 4-membered ring. And however, this 4-membered ring are not very stable, so you will not find the various example from them. If you have started your reaction with the 7-membered ring, then the ring contraction would be by 1 unit, and you will end up with the 6-membered ring, right, only when this carbonyl is the part of the ring. But when this carbonyl is not part of the ring, then there is no ring contraction. Okay, this is something very important which you should know. Later we will see the various example based on this. Okay, so in the first case you can see here you are using this alkoxide ion, so the ring contraction is happening here, and X, because it is the leaving group, so it will leave the system, and this C double bond O will convert into the ester. So this is your ester. Okay, so however I have missed a thing here, so it should be ester, so I should write OR here. Okay, so this is OR. Please remember this point. Okay, so this is your ester, and when you do use this OH negative, then again the ring contraction would occur. This 6-membered ring will convert into the 5-membered ring, and your acid will present in this chain. Okay, and if you use the amide, then you will have this amide side chain. So this is something very important which you should know. Now the important thing is that what kind of the attacking reagent we can use in that case. Later in the next slides we will see the what kind of the attacking reagent we can use. So this is your next slide, guys. Here actually I have made a difference between your Favoroski rearrangement and Favoroski type, or the Favoroski like rearrangement, and Favoroski like rearrangement are also known as the Quasi Favoroski rearrangement. So quasi means like alike, right. So it is when your mechanism follows through that Favoroski mechanism, but not exactly the Favoroski mechanism, then it is known as the Quasi Favoroski mechanism. So if you see here what kind of the substrate we can have. For Favoroski rearrangement we must have the alpha haloketones, right, that contains actually the alpha hydrogen, remember, and that alpha hydrogen will be present on the alpha carbon, and that alpha carbon which is having this alpha hydrogen would be different from the other alpha carbon which is having the leaving group. So what is the meaning of that? So this point you can see here. Say if I am having this one, this substrate I am having. Okay, so you know if you classify it, then you will find this is the alpha carbon and this is also the alpha carbon. Okay, the carbon which is just next to the functional group actually is known as the alpha carbon, and this alpha carbon, say it is having the Cl. So this is having the leaving group, however one hydrogen is also present here. Okay, and these two hydrogens are also present here in that case. Okay, so in that case you are observing the 3 hydrogen, but whenever you do the mechanism and if you want to remove the hydrogen as the base, so you will remove the hydrogen from that system actually, okay, which is not having the halogen, which is not having the leaving group. So the part which is having the leaving group, if you remove the hydrogen from here, so it will form a less stable carbanion. So this will not be your major product. So please remember this point. Whenever you have such kind of the system, you will always remove the hydrogen as the proton from the alpha carbon which is not having the halogen. This is a very important point. Okay, and if you go for your substrate for the quasi Favoroski type of the mechanism, then your alpha haloketones may not have actually any alpha hydrogen. So what kind of the substrate you can look for this? Say for example, for quasi type, right, say again I am doing this reaction, right, this I am giving you this starting material, okay, and this certainly having certain leaving group, and it is say this time it is also another leaving group is also present, say it is I, okay, and this is also actually logged by this say OR and OR. So you see here in any alpha position, right, this is alpha position, this is also alpha position. you are not having any hydrogen to it. So whenever your substrate is like that and you are having the good reagent for that Favoroski rearrangement, then it will actually follow the quasi Favoroski rearrangement. So first thing, alpha haloketones without alpha hydrogens, and sometimes it may also possible, this is the point actually which I want to emphasize, sometimes it is also possible if you have the any type of the alpha haloketone which have actually the alpha hydrogen, but the removal of that alpha hydrogen actually cannot be possible, may not be possible. That means you may also have your non-enolizable alpha haloketones. That means alpha haloketones having hydrogen, but it cannot form enolate ion, right. So later we will see this particular example, but for time being you should remember this point actually, right. So second thing is what? You are attacking reagent. So in most of the cases, right, see, out of 100, 99 times you will find this reagent, either your sodium methoxide with methanol or your sodium ethoxide with ethanol. So whether you are doing this Favoroski rearrangement or quasi Favoroski rearrangement, in both the cases the reagent would be same. And one more important thing, the product would also be same. So however, in the steps actually I haven't mentioned this particular point, but please remember, if you are doing the Favoroski rearrangement or the quasi Favoroski rearrangement, in both the cases the product would always be the same. Please remember this point. Then what kind of the intermediate you can expect? In the Favoroski rearrangement, you will always expect the resonance stabilized enolate ion. So this chemistry, you see, basically your carbonyl chemistry most of the time is dominated by the enolate ions. Okay, these enolate ions are very important, and previously I have discussed the reactions based on this also. But you remember this point, if you are going for the Favoroski rearrangement, it will actually show, it will form resonance stabilized enolate ion. Okay, and when you are doing for the quasi Favoroski rearrangement, then there is no enolate ion formation, the mechanism go in the other way actually. So what kind of the mechanism you may find in that case? So in case of the Favoroski rearrangement, it goes through the cyclopropanone step. That means one of the product will form in the reaction, that would be your cyclopropanone, and you know cyclopropanone is basically a 3-membered ring. So it is highly strained molecule. When it is highly strained molecule, it cannot actually sustain, so it will actually break under the influence of the nucleophile to give the different product. But when you are going for the quasi Favoroski rearrangement, then your mechanism would be benzylic type or the semi-benzylic type. So I don't have that much of time to explain the benzylic or semi-benzylic type of the mechanism. Basically it comes from the benzylic acid, right. So but I am not going to explain this one. I am assuming that this thing you actually already know actually, right. So these things you have to keep in mind. Now guys, from the next slide, I will discuss the plenty of the examples with the detailed mechanism for this Favoroski rearrangement. Please stay focused on the video. Please grasp the things completely, step by step. So I am starting with the very simple example, very simple example I am taking here. Say I am writing number 1, and in that case the substrate is actually, see, your usual substrate, which is this one. So this is the carbonyl group, and that carbonyl group is having chlorine as the leaving group. Okay, and in that case, if you do the reaction, say you know this is alpha haloketone. Okay, so that alpha haloketone, if this, and you know your substrate could be anything. So what I am doing in that case, I am taking, say in that case, NaOH. So I am taking sodium hydroxide. Please remember. Okay. And second step, I am also doing the protonation, because protic workup is always required, and to dissolve all these things I will need the alcohol. So I am also taking the ethyl alcohol. Okay. So what product would you expect in that case? I already told you, this is actually the alpha haloketones, and this carbonyl is present in the ring. That means the ring contraction would occur. That means your 6-membered ring would convert into the 5-membered ring. So definitely your product would have the 5-membered ring, just like that. Okay, and whenever you are using this OH negative, then it will convert into the acid. So simply you will write COOH. See this, how easy to identify the product is. But the important thing is that what kind of the mechanism actually it can give. So I am going for the mechanism in that case. So for mechanism, I am putting these 2 hydrogens here. These are the alpha hydrogens. Okay. And then you have used base for this one. This is OH negative. Okay. And I already told you this hydrogen is the acidic hydrogen due to the presence of this carbonyl group actually, right. This carbonyl group sucks the electron density from here, making this carbon hydrogen bond weaker. So, this hydrogen can be removed as the proton from here, right. So, when it will remove from here actually, so what it will give you, minus H2O, okay, and this electron pair will go onto this carbon atom, and then you will have here this species, carbon double bond oxygen, and this leaving group is present here, and this is negative charge which is present here. I am not writing another hydrogen to it. So, this is your enolate ion, and this enolate ion is actually the resonance stabilized. So, how the resonance stabilization you can show? So, this electron pair can come here and this can go up. Okay. So, guys, please remember, I am not actually putting all the lone pairs present on the oxygen, right. So, if you want, then you can put the 2 of the lone pairs over there. Okay. So, this is actually quite good for the beginners to understand the things completely. And if you draw the enolate resonance stabilized enolate, so this would be double, this would be single now, 1, 2, 3, 4, 5, 6, 1 is transferred. So, this is the resonance stabilized enolate ion. This is something very, very important. Okay. Now, what can happen in that case? In the next step, please see, this actually this negative charge will attack on this. So, it is type of your say SN2 type of the attack, right, and this actually not SN2, you can do the E2 type of the mechanism, right. So, because this halogen will remove from here. So, this will attack from this on this carbon atom, and this will leave from here. So, how you can show this thing? So, this will attack here, negative charge, and this chlorine will remove from here. So, when it will you will remove this from here, what you end up? You end up with this species which looks like just like that. This is oxygen. Okay. So, you see the 3-membered ring formation actually has taken place here. So, if you want, then you can number it, say this is 1, this is 2, this is 3. 3-membered ring, but remember this 3-membered rings, this cyclopropanone system is actually not very stable. So, if actually some nucleophile is there, then the nucleophilic addition would occur to give you the product. So, how this nucleophilic addition would occur? Say for this actually I want to remove this one, and this is also, and I am removing this one, and say you are having your H2O, you have taken this water here in the reaction, and this water you have also formed in this particular step. So, what can happen? It can attack on this carbonyl carbon nucleophilic addition, this can go up, and when this will go up, you will end up with this kind of the species. This is your 6-membered ring, there is no problem in that. This is 3-membered ring, and this would become negative, and this will have your O, H and H. This is positively charged species, this is lone pair. Why this happens? Why this had happened? You see, this has when this will attack on this carbonyl carbon, this electron has moved up. So, this will become carbon single bond oxygen with negative sign, which I have drawn here, and this these 2 lone pairs actually will be donated to this particular carbon to form a bond. So, it is bond formation is taking place, and that is why this is positive charge is there, because it has this oxygen has lost this electron pair to form a bond. Okay. So, this is how you can see you can do the reaction, right. Now, what happens in the next step? Right? In the next step, this will come back onto this one, and now you have to decide the breaking of the bond. You can break, see, because this cyclopropane ring has to cleaved. So, you can break this particular bond, or you can break this particular bond, right, and you will put the negative charge on one of them. So, in this case actually what I am doing actually in that case, I am removing say this bond, and I am putting the electron pair here. So, what you can have in the next step? So, you will have this 5-membered ring, there is no problem in that. Okay. And then you are having this double bond oxygen, and then your oxygen, hydrogen and hydrogen. The upper part I have written in the simplest manner, and this bond is connected here, and this has cleaved. So, this will put negative over there. See how easily I have done this. This is doubly bonded carbon, this is doubly bonded carbon, and this is having this part, and this has braked and putting the negative here, and this has connected here. Okay. So, this is the carbene ion present in it. So, if you have cleaved this particular bond, again you will if you have cleaved this particular bond, you will form this carbene ion at this end, but both actually are the symmetrical one. So, it does not matter whether you form bond with the you form an carbene ion from this end or from this end, this will not make any difference, the product would remain the same. Okay. So, now what would happen in the last step? So, last step is the proton abstraction. So, how the proton abstraction would occur? So, this negative charge will grab one of this particular proton and pushing back this electron pair over there. So, hydrogen will come here actually. Basically, it is the Protic workup. It is the Protic workup. Okay. So, what will happen? The hydrogen would come here and this will become you see carbon double bond oxygen and this is OH. So, this is OH, COOH and this is 5 membered ring. Okay. So, however, I have made the product in the different way and here is the different way, but these two will actually the equivalent one. So, this is something very important which you should know. I hope this is clear to you. Now, what we can do, we can take one more example which actually would be different from this particular one, and this will give you the immense this example actually will give you the immense insight into the mechanism and the various things of the organic chemistry. Say you are having this species. Okay, this is another very example. I did not find, see this example actually I have made by my own and I did not find this example from any book, but this is the exercise actually which I have done. So, I am not sure whether in the lab you will be able to perform this or not, but it is quite good or an interesting example, right. Say this is having I and this is having hydrogen, okay, and here this is having chlorine and this is having hydrogen, right, you are having this one. So, what actually you will form in that case? Say for example, what you are doing, you are taking this, say your reagent in that case is sodium methoxide NaOMe along with the MEOH. So, what you expect in that case? Again you see this is the 6 membered ring which is having the carbonyl system. So, if you do the Favoroski rearrangement, so this will actually reduce the this will actually contract this 6 membered ring to the 5 membered ring. So, what you will have in that case? You will have 5 membered ring. There is no problem in that. Okay. And since you are using this OMeOR, so this will convert into the ester. So, say you are having this ester in that case. This is double bond oxygen, okay, and this is OMe and double bond. You have produced this thing actually. Okay. So, how we can explain the mechanism for this one? Say for example, you are having this base, okay, MEO negative. So, what it will do? It will actually abstract the proton either from this end or from this end actually to form the enolate ion. But the problem is that this iodine is also the leaving group and this chlorine is also the leaving group. Both are the leaving groups. Please remember this particular point. Okay. So, but you know this I is the better leaving group. So, I can write, you know, this is the better leaving group because it can stabilize the negative charge pretty well due to its bigger size. So, it is better Lg than your chlorine. This chlorine is not better Lg. That means now it is quite clear, as I already told you, you will remove the hydrogen as proton from that alpha carbon which is not having the leaving group. But you see this I is the better leaving group. So, this is the leaving group. So, you cannot remove the hydrogen from here. So, you will remove the hydrogen from this one. And another thing you may consider also, chlorine actually is this chlorine is having the higher your minus I effect. So, this will make this bond weaker. But the previous explanation is quite good actually, in which you are saying that this I is the better leaving group. Okay. So, how we can go for this one? So, this will remove this hydrogen from here and this will push the electron here to form the enolate ion, and when you have the enolate ion, then you will have this species, and I can draw the that species just like that. Please follow. This is double bond O, okay, and this is the chlorine and with negative charge. So, I am not drawing the resonance stabilized species for this one. Okay. So, you know this enolate is resonance stabilized. So, in the next step your 3 membered ring formation would occur. So, how the 3 membered ring formation would occur? This negative charge will attack onto this carbon and this I will leave from here. So, you can write minus I negative and then you can have your species just like that. This is 3-membered ring, and this is just like that, and it is having the chlorine, okay, and you have this species. Now what can happen in the next step, guys? In the next step you are having this OMe again, okay, that is nucleophile. So it can attack on this carbonyl carbon, pushing back this here, this lone pair over there, and then you end up with this species. This is your 3-membered ring with 5-membered ring here. This is your chlorine, this is your O negative, this is your OMe. This is the next step. And what can happen in the next step? Okay, so in the next step it's quite easy here. You see here what you can do. See, this electron pair will come here. Now you have to break the bond. Now you have the choice whether you break this particular bond to form the carbon ion and add this particular species, or you break this particular bond to form the carbon ion on this particular species. But I am removing this bond which is not having the leaving group. Please remember, this chlorine is the leaving group. So whenever you have this situation, leaving group is there, you will break the other bond, right? Because this chlorine actually, by donating electron pair to this system, will destabilize the carbon ion. So you cannot break this particular bond. So I am breaking this bond and pushing the electron density here, and when you do this, then you will have this species. This is your Cl, okay. This is double bond, this is OMe, and this is negatively charged species, okay. See, please remember, if you put the negative charge over there, so this chlorine is also having the lone pair, so this can push electron density over here. This will not make a resonance very good stable carbon ion actually, okay. So in the last step, what can happen? This can come here, and this chlorine also leaves from here. So if chlorine leaves from here, Cl negative, what will happen? You see, this would become double bond. So this is the double bond present in it, and that would be your COOMe. So this is COOMe, right? So this actually is having this question is having the very good concepts actually of leaving group or acidity, right? Both of things are there in that case. Now moving to the next problem, what it says, say see the two problems which you have seen actually are quite common in your say JEE examination, whether it is JEE mains or the JEE advanced. But when it comes to the CSIR net or the GATE examination, you have to consider the stereochemistry of the product also, okay. So the third example actually is explaining the stereochemistry also. So say this is your third example, and that third example is having this carbonyl system. Please remember, this is double bond oxygen, and this is I, and this is your tertiary butyl group, okay. And please remember, this is beta, this is also beta, and in the stereochemistry terminology, you know, beta is above the plane, above the plane. So it is saying that this actually tertiary butyl group, which is the locking group, which will lock this molecule in one configuration, so that the flipping will not allowed, and when the flipping is not allowed, you end up with the pure product actually, side reaction would not be there, okay. And this is also at the beta position, okay. And what you are doing the reaction with this one, and you are taking the famous reagent, that is NaOMe, and with the MEOH, right? You are taking this one, okay guys. So what you end up, again the important thing is that this 6-membered ring is having the carbonyl group, so this ring contraction would occur in that case, okay. And you are using this, so you will form the ester, okay. So how the product look like in that case? So it's quite easy. Make this 5-membered ring, okay, and convert this carbonyl into the ester. This is double bond O, this is OMe, okay, and this will also, this T butyl group is also present here at the beta position. So here also it is having the beta configuration, that means beta orientation, and this is also the beta orientation, Okay. So, now how actually we do this particular reaction? See, whenever you have this 6 membered ring, then it is quite easy to draw the cyclohexane ring. So, what I can do for the mechanism actually, so I can write the mechanism here. I can write the mechanism here. Okay. So, what I am doing here, say this is my 6 membered ring. So, this is just like that. So, to make it little bit more clear, what I can do, I can give it this 1, 2, 3, 4, 5 and 6 membered ring. Okay. So, this is your carbonyl. Okay. And at position 2 you are having I. So, what you can do, you can put I here, equatorial. Okay. And that at your say position 1, 2, 3, 4 you are having this tertiary butyl group. This is something very important. If I want to put the number, this is 1, this is 2, this is 3, this is 4, this is 5 and this is 6. Please remember. So, how actually I have drawn this one? See guys, I have made a extensive lecture series on the conformations of cyclohexane and the decalene systems. Okay. If you haven't watched that video and you have some doubt in understanding these things, so I am giving the link in the description, go through the videos also. But for time being I am explaining you, this is beta, that is above the plane, right, and this is also above the plane. So, I am putting intentionally this I above the plane related to this configuration, this, right, and again you see this is also beta, that means it is above the plane. So, I have to put this is above the plane, right, and this is also this, because this is the bulky group, it has to be equatorial and this will lock the molecule in this particular position. Okay. No flipping would be allowed in that case, you will have the pure product in that case, right. Now quite easy. So, now you see here you are what I am doing, I am marking this. Okay. So, this is your alpha carbon and this is your also alpha carbon. Okay. So, this alpha carbon is having the leaving group. So, this is leaving group and this alpha is having the hydrogen here. Okay. 2 hydrogens here. So, I am writing 2 hydrogens. Okay. So, what can happen in the next step? See, you are taking this OMe in that case. It is acting as a base. So, what can happen? It can remove this proton and pushing that bond onto this carbon, alpha carbon, to form the enolate ion. So, how the enolate ion will look like in that case? So, I am drawing the enolate ion. Please wait. Okay. Just like that. Okay. This is your carbonyl system. This was your I. This was your T butyl, and this was your negative charge. So, what can happen in that case? Favrovsky type of mechanism you are doing. So, the elimination would occur. It will attack onto this carbon to form a 3 membered ring and this I will leave from here. So, what will happen? Minus I negative and you end up with this species. Okay. And you see this is the 3 membered ring which you have formed. This is the double bond. Okay. And this is your tertiary butyl group. I hope there is no problem in that. Okay. Now, in the next step, what you are taking your OMe, right. So, that OMe can attack on this carbonyl carbon. So, this will come up. So, what can happen in the next step? Next step, you can draw this thing, okay, just like that. There is no problem in that. Okay. So, this is this one. And this would be O negative now and this is your OMe. So, what can happen in the next step? This will come here, okay, and you have to break a bond. So, what you have two choices, you have to break this bond or you have to see, you can break this particular bond or you can break this particular bond. Okay. So, it will not make any difference if you break this bond or this bond, because product would always remain the same and ring contraction would occur in that case. So, for simplicity, to show you the clear mechanism, what I am doing, I am breaking this bond and pushing the negative charge over there, putting the negative charge over there, not pushing. So, what can happen in that case? You are having this species now, okay, and you will put the negative over there. Fine, there is no problem in that. This is carbon, this is double bond O and this would be OMe. Now, see here guys, earlier you are having the 6 membered ring. How? See, this was 1, 2, 3, 4, 5, 6, but when you broke this particular bond, so now you left with the 5 membered ring. So this is your 5 membered ring, guys. 1, 2, 3, 4, 5. In the last step, what you do, you the Protic Workup. So I am writing Protic Workup. Protic Workup, and this proton obviously will come from the MeOH. Please remember this point. So this negative charge can grab this proton from here. So what you end up? You end up with this species, 5 membered ring, and this is OMe, and this is equivalent to what? Just like that. Okay, and I forgot to put this. Very sorry, I forgot to put this. So I have to put this over there. Okay, and you see here also in the product, I will put this above the plane, just like that. Okay, and then you see here this actually will go also up. This is C double bond O OMe. So you have to actually decide the stereochemistry also. This is something very, very important, right? So this is above the plane. You see here in that case, when it is breaking, when the bond has broken, so this is above the plane. Okay, so that's why you have to put this above the plane. That's why I have put it this above the plane. So this is how you can draw the mechanism for this one. The key thing is that you actually need to know how to draw the these things actually. And one very important thing actually which I forgot. So what I am doing, I am making that thing here. You see in this particular step, this step actually, this last step where I have removed this one, right? So actually what here you see this negative charges are taking here. See the configuration of this, right? This and this and this relation, if you see here, this negative charge and this leaving group must have this relation, anti-periplanar relation. This is very important. So I am writing here anti-periplanar relation, anti-periplanar relation. For the elimination to occur, actually this negative and this leaving group has to be in the same plane, and also they must have the anti configuration, that means trans. So this is going in that direction, this is going in that direction. This thing is very, very important to close the ring in this form actually, right? And this is possible in that case. Okay, see the important thing is that if you have this configuration, so I can use the next page. I hope this is clear to you. If I use this thing, okay, so you are having this double bond O, and this is B, this is alpha, okay, Br, this is the leaving group, okay, and this is your beta. So this is alpha, this is beta. So if you do the reaction with this one, actually, if you use the NaOET in that case along with the ETOH, so there would be no reaction. Why no reaction? So you can, I am forming this carbon ion for this one, that enolate ion. Okay, so this was your carbonyl, please. And this is, see here, this is actually your alpha, that means below the plane. So you have to put this Br below the plane. So what you can do, you can put this Br as below the plane, and this is negative charge. Okay, and if you check the relation would be cis periplanar, right? Cis and anti periplanar. They must be in the one plane, but it is going down actually. It is below the plane. So they are not in the same plane. So in that case, the ring closure would not occur in that case. So for this stereochemistry, the product is not possible actually. Okay. So again, this is very important. Now the next thing, the next example which we can check, that is the example number 5. Up to 4 I have done actually, right? This was, you can consider as 4th. So in the next example, I am giving you this species. Say again a 6-membered ring I am giving to you. There is no problem in that, but here I am making a little bit difference in the group actually, right? And this is having CH2Br. Okay, and of course this is the locking group, tertiary butyl group. And if you do that Favoroski rearrangement with this, So, again I am taking the same reagent NaOMe, and that NaOMe in presence of the MeOH. So, what would you expect in that case? Your product would be like that. Of course, you are going to form the ester in that case again, okay, and that ester would be in this position. This would be OMe, and this carbon will have 1 methyl which is below the plane, and of course, this is tertiary butyl group. So, this product you are forming. So, in that case guys, you can see here, of course, you are using the OMe. So, ester will form, the ester is forming, but here no ring contraction. Please remember, no ring contraction. Why no ring contraction? Because this carbonyl group is not present in the ring. Ring contraction only occurs when this carbonyl is present within the ring. Please remember this point. So, if you want, then you can easily go, you can easily draw the mechanism for this one also. Since these things are very important, so I am drawing the mechanism for this one also, and for mechanism again I am doing the same thing. I am making this Csir form, guys. Okay, so this is where tertiary butyl which I am putting here, and this position you are having this system, that means you are having this O, your CH2 and your Br. This I have taken, okay, and of course, in that case you are having the hydrogen, and if you do the reaction and you are using the OMe, so this will grab this proton from here, pushing this electron pair over there, and then you will have this species. Very quickly I will draw for you, just like that. This is carbon double bond, this is CH2, this is Br, and this is your locking group, okay, and negative charge. So, what can happen in the next step? 3-membered ring. So, it can come here, this will knock out this. So, minus Br negative, and you end up with this species, this T-butyl group above, this is strained 3-membered ring, okay, and then again you have used what? OMe. So, nucleophilic addition would occur, this will come here and it will push electron over there. So, what can happen in the next step? You are having this species, just like that, putting 2-butyl over there, and this is O negative, this is OMe, this one, okay. Now, in the next step, now this step, guys, is very important, you need to understand, okay, you need to understand this one. So, this will come here, and now you have two options to break the bond. You can break this particular bond, you can break this particular bond, okay, but intentionally I am breaking this particular bond. Please remember, I am breaking this particular bond. So, this will remove, and you will have next species which will look like this is T-butyl going up, this is just like that, and this is your carbonyl, this is OMe, and this is negative charge over there. So, guys, please remember, this is actually your 1 degree carbanion, 1 degree carbanion, and if you have see, if you have broken the bond from here actually, so this will put negative charge over there, and when we put the negative charge over there, so this would be 1, 2 and 3, this would be tertiary carbanion. So, putting negative charge over there will produce the tertiary carbanion, and you know the tertiary carbanion is less stable than the primary one. That is why I have broken this particular bond. So, in the last step, what you do? You do the Protic Workup, and that Protic Workup would come from this methanol, okay. So, this will grab hydrogen from here, and you will end up this species. This is up, and this will become now CH3. okay, and this is what O, this is OMe, right. CH2, see, remember this is this part is simply carbon and that carbon was CH2 actually, okay. When you break the bond, this would be CH2 negative. That is why grabbing one hydrogen from here will convert it into the CH3, okay. Now, if you see this here, this is beta, tertiary butyl group, this carbonyl part is also beta and this methyl is the alpha. So, if you draw the proper normal 6-membered ring, so you can draw this in that manner, okay. So, this is your ester OMe, and just after ester you are having this methyl which is below the plane. So, you will put that methyl below the plane Me, okay, and after that you may have your next orientation of this T butyl group which would like that, okay. So, if you see here, this species is nothing but this is this one actually, right. So, no ring contraction occur in that case. See how easy the question is actually. Now, very quickly we will move the next. See, the length of the video is going to increase, and don't worry about that, don't worry about the length of the video, try to understand the things actually, okay. Now, say next thing actually, now I will not draw the mechanism for this one, I am leaving the mechanism for you, you try it by your own. If you do not find the solution, then you can comment in the comment section, I will give you the detail of that mechanism also. So, here in that case, my next problem, say my problem number 6, in the problem number 6, say you are having this species, right, this species, and here you are having the nitrogen, and that nitrogen is connected with CO2 ET, okay, and this is your carbonyl group, please remember, okay, and here stereochemistry is not defined, this is leaving group Br, okay. You have this species. So, what you can do, you can count the number, this is 1, this is 2, this is 3, this is 4, 5, 6, 7, 7-membered ring, guys, please remember 7-membered ring. And this is alpha carbon which is having the hydrogen, this is alpha carbon which is having the leaving group, that means you can form the enolate from here. This is quite sufficient for the Favoroski rearrangement, okay. Obviously, the ring contraction would occur. So, in that case also, if you do the mechanism, say I am drawing this mechanism again with this NaOMe with MEOH, okay, you can write in that manner, okay. And after that, see, let me check, previously I had made some mistake. Yes, no, fine, no, okay, ठीक है, right. So, what product you can expect? You can expect the 6-membered ring. So, how you will draw the 6-membered ring? It is quite easy. This is a 6-membered ring, okay, and that is nitrogen, and this would be your CO2 ET, fine, and that part would convert into CO2 Me, ester. You are converting, what you have done actually, you have converted this carbonyl part into the ester part, right. If you count the total numbers, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So, ring contraction has taken place. You have formed 6-membered ring. So, if you want, then you can go through the mechanism by your own to understand the things actually, right. So, I am not going to draw the mechanism. Now, going to the next problem, what I can have actually, okay. Next example, say I am taking this one, problem number 7. So, again I will not draw the mechanism, but I will give you the hint. This is O, this is Br, and this is CO2 Me already, and this is Br. So, it is having the two leaving group, two leaving group. One is Br on this alpha carbon, and one Br on this alpha carbon, but this alpha carbon is also having the hydrogen. So, obviously, you will remove the hydrogen from here to form the enolate ion in that case, okay. But remember, whenever you have the two leaving group present on it, then your system actually the contracted system, this 6-membered ring will convert into the 5-membered ring, and that contracted system will also have a double bond. This is the thing which you have to remember, and this is the trick also. This is NaOMe, and you are doing the reaction with the MEOH, you will end up with the 5-membered ring. So, I am drawing that 5-membered ring here, say just like that, and at this position what I am doing, I am converting this into, say, let me check what I am having. Okay, at this position I am also having the ethyl. Okay, so you have to put the ethyl here and double bond here, and this part will have CO2Me, this will also have the CO2Me. So, this is important, right. So, whenever you have the two halogens actually, see this type of problem I have already solved in the previous example. Let me check where I have solved this. No. Okay, this one. In this problem you see here one halogen is one leaving group is here, one leaving group is here, and you end up with this species. Okay. So, obviously in this particular example also here you will end up with this species. So, this is where see this is how you can do the things actually. So, this is all about your Favrovsky rearrangement. Now, very quickly we will look the some more problems based on the quasi Favrovsky rearrangement. So, now I am going for the quasi Favrovsky rearrangement. Quasi Favrovsky rearrangement. And to do the honors, this should be capital F, Favrovsky rearrangement. So, in that case I am giving you the mechanism or reaction rather. Say this is quasi, okay, this, and this is your Cl, and this is your carbonyl, and that carbon is also having the phenyl. Okay. So, in that case you see here this carbon is alpha carbon, which is not having any hydrogen over there, and this at this alpha position you are having the phenyl. So, there is no question of the hydrogen. So, that means the enolate chemistry will not occur from here. So, if you do the reaction with this say you are having this base, in that case this base will obviously act as the nucleophile. Please remember this point. Okay. So, what do you expect? It will attack on this carbonyl carbon, it will push this over there, then you will have this species. This is the 6-membered ring, okay, and that part is having this leaving group here, and this is O negative now with this pH, that is phenyl, and then your OH has attacked over there. Now, this step is very, very important. In the first step, what will happen? This will come here. Okay. So, this carbon would become pentavalent now. See, this is singly bonded, this is singly bonded, but after this moment this would be doubly bonded. It's a 2, 3, 4 and 5 pentavalent. So, it has to regain its tetravalent state. So, this is actually see the elimination type of the reaction. See, substitution, SN2 substitution. So, this will attack on this carbon and the Cl will remove from here. So, this is SN2 attack. Okay. So, SN2 attack, that means the reaction goes through the concerted mechanism. So, what can happen in that case? This was your 6-membered ring now, and this phenyl would be placed over there, that carbon is present already, this would be double bond now, this would be OH. So, you can expect this particular product. Okay. So, this is the product. So, again you can see here this has attacked over there. So, this will make this species. Now, this will come here. So, this will move from here to here, SN2 attack, and this is actually leaving here. So, this is quasi Favrovsky rearrangement, Favrovsky like rearrangement, but not exactly the Favrovsky rearrangement. In that case, no enolization would occur. Very important, very beautiful reaction. Okay. Now, what we can do? We can go for some important reactions, and those reactions actually, say for example, I am doing this one. So, guys, for simplicity I am doing this one. Say what I am doing, I am taking this example from CSIR net 2019 December, but I am not going to actually solve the detail all the complete reaction, but I am taking the part of that particular reaction. Say for example, I am doing for the quasi Favoroski reaction. Okay, say you are having this one. This is the 6-membered ring, okay, and this carbonyl is present here, and with this carbonyl you are having this species also. Just like that, okay. Say you are having this, okay, and here you are having this methyl substitution, here you are having this double bond, and here you are having this Br as the leaving group, and here you are having CO2 Me. So, this is the product actually formed in this CSIR net examination in the intermediate stages, but I am going for this one only, okay. So, and the reagent you have been given, this is P double bond O, right, and then CH2 Li, lithium is there, and then OMe whole twice, this you have been given. You know, carbon being more electronegative is negatively charged, and of course, this is positively charged. That means it can act as the carbene ion or simply the nucleophile. So, what can happen? Nucleophilic addition. It will attack here and this will push this up actually. So, I can use this color, this, and you will push this up, okay. So, what you end up? So, you will have this species, right. Okay, let me draw it little bit below, otherwise the things will become complicated. This was your 6-membered ring. Now, this would be your O negative, okay, and that would be your, so little bit elongated bond I have drawn to actually explain the mechanism, and this was your OMe whole twice, and rest of the thing I will not touch. This was your Br and this was your CO2Me, and that part is also having this thing, okay. So, let me delete it actually, it is not looking pretty beautiful. So, I have to remove this, and now you see here I am drawing the remaining part just like that, okay. So, this was your double bond, this was just like that, okay. So, now what can happen in the next step? Now, you have to break the bond. So, you can either break this particular bond and you can break this particular bond. So, this is the leaving group, right, this is the leaving group, and since leaving group is leaving from that carbon, so you cannot break this bond. So, I am breaking this bond. So, I am breaking this particular bond here. See, this will come here, okay, and I am breaking this bond. It will attack here and this will leave. So, what will happen in that case? The Br will remove from here, Br negative, and what you left with, since you are doing that your CSI net examination question, and in that case you see the ring contraction would occur, and for the ring contraction you can count the total electrons. See, this is actually, see, 1, 2, 3, 4, 5, then 6, 7, 8, 9, 10. 10 are there, so you can make 2 5-membered ring. This is one 5-membered ring, this is another 5-membered ring, and this 5-membered ring will have this one, and this will have CO2 Me as you can see here, this was already present over there. Okay, this is already present over there, and now you will have this C double bond O, then P double bond O, OMe whole twice. How? See, this has moved, so this will become carbon double bond oxygen. So I have put it that carbon double bond oxygen here, and this is linked with this carbon. So this is with this chain actually, right, with this ring actually. So I have drawn this in that manner. Now when this bond will break, so it will bring this part out of the ring. So this part actually, you see here, this is having the carbonyl, this is also having this part. So carbonyl, this part and that part. So this is how you can do the mechanism. Okay. So but this was the question actually. Now what we can do, we can go further, we can do more problems based on this. Say my next problem is this one, which is say this, let me check, right, this say you have been given, okay, and this is the carbonyl system which is present here, and this is the leaving group Br. Okay. Then if you want, then you can number the system also, 1, 2, 3, 4, 5, 6, 7, 8. So total 8 carbons are there. Definitely when 8 carbons are there, then you will do the reaction just like you did here actually. See, this was your 8 carbon system. In the 8 carbon system, you have contracted this 6 membered ring to the 4 membered ring, and this was already 4 membered ring, and you have the fusion bond in between them. Okay, right. So this is how you can do. So what can happen in that case? Say I am having my ET, OET. This is negatively charged. See, this is actually non-enolizable ketone, non-enolizable. That means you cannot form enolate with this. Okay. However, see, this is having the alpha hydrogen. See, if you see here, alpha hydrogen is present there. But you see, the important thing is that if you remove that hydrogen and putting negative charge there to form the carbon ion, this would be sp3. And when this is sp3, so this cannot be coplanar with this carbonyl, so the conjugation is not possible. So that's why enolization would be difficult in that case. Okay. When enolization is difficult, please remove this. Okay. And then in the next step, what can happen? It can attack over there, it can go up. Okay. So in the next step, you are having this species. I am drawing this again. This, and this, just like that. Okay. And that part now is having O negative and OET. There is no problem. This is your Br. I think there is no problem in that. Now you have to remove the Br. So what you will do in that case? So you have to break the bond. So this will come up, come down, and this will actually join this carbon, and this chlorine will remove from here, this bromine will remove from here. So minus Br negative. Now if you clearly focus, see, this is forming one chain. From here actually it is forming one part actually, right, and that part would be different. So 2 ring you will form in that case. So if you want, then I can give you the number also. Say for example, this has formed bond with this one, because this will form bond with this one, right. So if you want to number, say this is 1, 2, 3, 4 and 5. Again for this one, say this is 1, 2, 3, 4, 5. So 2 5-membered ring you will form in that case. So how? I can say this is one 5-membered ring and this is another 5-membered ring. Okay. And if you do the numbering for this one, say I am doing in that manner, say this is 1, this is 2, this is 3, this is 4, this is 5, or simply 1, 2, 3, 4, 5. So, this actually linkage is what? Your 4-5 linkage, 1-5 linkage, and at the 1-5 linkage, that means at the position number 5 you can see here, at position 5 you are having this part, ester part. So, what you can do, you can put simply this part here, double bond O ET. So, again this is the beautiful example of quasi type of the Favoroski mechanism, where enolization is not possible. Okay. So, this is how you can solve the variety of the problems. See guys, I am having the very large number of the problems, but it is not possible to solve all the problems. So, I am not going into that much of the problems, but I can give you say one more example, one last example which have been asked in the CSIR net examination in 2018, and then I will complete this. And question was just like that. See, I haven't written that particular question, right. See, you have been given two compounds, right. One compound, say this question actually December 2018 CSIR net. Okay. So, you have been given two compound, one chloro, one phenyl. Okay. Propanone 2, propanone 2. This was the first compound. Second compound was 1 chloro and 3 phenyl. 1 chloro, 3 phenyl, propanone 2. These two compounds were given actually, right, and they both actually are undergoing the Favoroski rearrangement, FR I am writing, and they are giving the product A. Okay. So, you have to identify the product A. So, what we can do, we can draw the say structure of this one. So, first one you see propanone 1, 2, 3. Since it is the propanone 2, so at the position 2 I am putting propanone, and at this position I am putting the chlorine, right, and hydrogen here, and phenyl is also there. No, not what we can do, one position having chloro and phenyl. So, I can write pH also here. So, I am writing the phenyl here, and that is CH3. Okay. This was your first compound. Second compound, they are having C, this is propanone 2, okay, and 1 chloro and then 3 phenyl. So, that means pH. So, it is also doing the Favoroski rearrangement. That means you simply say, for example, for Favoroski rearrangement, say you have been given this OMe. Okay. So, what this OMe can do? This can form the carbon ion from here, and similarly in that case also, this is OMe, it can abstract proton from here. So, in both the cases, you actually in this particular case, you can form CH with negative. Of course, the phenyl is there. This is C double bond O. This is CH2. This is Cl. Okay, this you have formed. In that case also, you have been formed CH2 negative. This is double bond O. This is C, Cl, pH and H. Now, the ring closure would occur. How the ring closure would occur? So, this will come here and this will come here. So, in both the cases you will have the product double bond O with this, and it is having the phenyl, and of course, this will leave minus Cl negative. So, this is the product. In that case also, this chlorine will leave and you will have this product. Okay, and phenyl is here. So, you see these two are actually equivalent. So, question was that identify A. What was the A actually, right? So, in that case your A is clearly you can see here, your A is in the question actually itself, it is given your A is your question, your say option D actually. So, how you can go for the option D? Say they are having the both species, and in both the cases you have made this pH. Okay. Now, say you are having the OMe again. So, you can attack it here and you can shift it over there, then obviously you will have this pH I am writing in that case, this is O negative, this is OMe, and in the last step you can push it back. Okay. Now, you have to break the bond and it is up to you. So, say for example, now I am breaking this particular bond. So, what you end up? You end up with this double bond oxygen, this is OMe at the top, this and putting negative over there, and this is pH. So, this is resonance stabilized enolate, resonance. Okay, resonance stabilized enolate. So, in the last step what you can do? The Protic workup. In the last step, the Protic workup. Protic workup. So, what can happen? If we have taken the MEOH, so this will grab hydrogen from here and you end up with this species, this is OMe, this and this is pH. So, if you want to do the numbering for this one, okay, then what you can find here, say this was 1, this was 2, this was 3. Okay. So, at one position you are having methoxy, at 3 position you are having phenyl, and this is propanone, propanone 2. Okay. So, this is actually the A which actually they have asked in the question, and you have been given 3 options and that correct option was present in the option D actually. Okay. So, this is how you can solve the problem. So, guys, I thought that I will explain more problems to you, but see the length of the video has increased so much, it is almost around 1 hour 12 minutes. So, I am stopping here, and if you want to learn these things, then you can go through the various books to actually grab the knowledge about the Favoroski rearrangement and the Quasi Favoroski rearrangement. So, there are various reactions which have been asked in the previous year CSIR net examinations also. You can go there and search it. So, I hope you like the lecture and you understood the things completely, okay, about your Favoroski rearrangement. Okay. So, if you like this, your understanding, please subscribe the tetrahedron chemistry classes. Don't forget to like the video. Do share with your friends also. Okay. So, that's it for today. Thank you very much.